Hi everyone, welcome to the last session, and the room is getting more crowded. But yeah, let's get started. The last session is gonna be with one talk by Ralf here, and another remote talk, and then panel session. So, as the first speaker of this session, let's welcome Ralf.
Yes, mic check is also working. Great. Yes, thank you all for coming and exploring this room. Apparently Rust is very popular. That's great. So let's talk about specifying Rust. So you've probably all heard of Rust, and the main thing you're going to have heard about it is, I mean, it's known for its type safety, right? You get this nice high-level type system for language that still supports low-level paradigm, and that's all great, and it's a happy land, and our little Ferris crab can live very safely there. But what you might have not heard is that Rust has a dark secret side. And this dark secret side is unsafe Rust. So as long as we only talk about safe Rust, the runtime semantics are kind of obvious. I mean, they're not really obvious. There's still a lot of things going on, and we heard a bunch of talks earlier about specifying entirely safe language, and it's complicated. But Rust is like, it's the same kind of problems. And generally everybody kind of agrees on what all the programs would do. The hard parts are more like type system, borrow checking, pattern matching, like there's a bunch of gnarly things there. But when we go to unsafe code, then even just the intended runtime semantics of code can get tricky. So it's kind of a different dimension of the problem that, like for example, SpecTech has been solving. And so to explain why that is, I brought two demos of like the kind of weird things that can happen when you have fun with unsafe Rust. So here's a first little demo, which creates an integer by illegal means, namely by just taking some memory which is not actually initialized and just saying, yeah, don't worry, there's an integer here. And then it tests a rather innocent property on that integer, namely that it's less than 0 or equal to 0 or greater than 0. And if you compile this with the latest, okay, this is no longer the latest, but same with the latest Rust compiler, same result, we see that somehow the assertion actually fails. So I think we need to call our mathematician friends because we discovered a new integer. So something very strange is going on here. So that's the first demo. And then there's a second demo, which is a bit more spicy because it involves pointers. And so what we have here is I'm going to go over this program well, as slowly as I can. So we start with two local variables, 0 and 1, initialized to 0 and 1, and we get a pointer to both of them. And I helpfully named the pointers after the variables. And then we do a few shenanigans here, which boil down to computing y plus x minus y, which of course the two y's cancel out. So this is basically just x, and we use wrapping arithmetic, so there's no weird like hidden overflow nonsense or anything like that going on here. This is really just y plus x minus y. And we can even confirm that, yes, those are actually the same pointer. And then we write through one of these pointers, and we read through the other. And because it's the same pointer, obviously we should get the result, right? Except if we build this program with optimizations with the latest Rust compiler, we don't. We somehow still get a 1 here, even though we've already written 2 to that place. So again, something weird is going on, right? There's a dark, that's why there's a kraken in unsafe Rust. It can really turn your program into some very, like doing some very strange nonsense. And so some of you will have already guessed it. What actually happens here, of course, is that these are examples of undefined behavior. And once you have undefined behavior in your program, afterwards, like any kind of garbage can happen. So the main challenge when specifying unsafe Rust is to carve out exactly when our program does and does not have undefined behavior. There's generally, usually consensus on what happens on the happy path, but whether we are on the happy path is unclear. And so if you wanted to look for some inspiration for how we could write such a spec, we could go to some prior work. There's like, I mean, WASM and all the other nice languages we discussed don't really have undefined behavior, so unfortunately we can't just copy what they do, but C and C++ do. And it turns out what they're doing doesn't really work. So there's a lot of work not teasing this out, but particularly a lot of this paper where they kind of went ahead and just asked a bunch of programmers about what they think about various parts of the standard. It turns out there's really 3 versions of the C standard. There's the standard version, there's what the compiler implements, and that's what the programmers think, and those are just like 3 completely different languages. And so I think currently if you're claiming you formalized the C standard, I don't think you can really make that claim because the standard is so ambiguous and it's so unclear which part it has to do with the real world that you formalized something, but you have not formalized C as it is in the real world or C as it is in the compiler, because those are not even the same thing. So there's work to be done even figuring out the standard, the spec, before we can formalize it. And so we have the similar problem in Rust. We need to figure out our spec first. And so I want to list a few desiderata for this spec, which I can go over very quickly because they will be completely uncontroversial in this room. We want it to be precise and executable. Everybody already said that today, so I can skip this part, which is great. I also want it to be accessible, because I want this to be kind of eventually become part of the Rust specification. I want Rust programmers to be able, at least the advanced ones that are writing unsafe code, to be able to deal with this. We cannot litter this with Greek letters, right? Nobody can read the spec there. So we have to do something which is both precise but also accessible to Rust programs. It doesn't have to be accessible to anyone. We can assume they know Rust. Of course, I want it to be complete because it's actually supposed to be the spec of the language. And eventually, I hope this can become an official part of the Rust specification as produced by the Rust project. So how are we going to go about this? So my proposal for how this could work is MiniRust, which is following this core language approach, which also has been kind of successfully used in a bunch of prior approaches, including, I would argue, some of the great JavaScript work we saw earlier. This like fragment of English that's basically formal is kind of a core language that they use to describe these individual operations, right? So in our case, the core language is a formal one, but I think this is a very successful approach to break down large operations into a series of small operations. And we're actually kind of doing this on 2 layers even here. And the style of MiniRust is that it is an operational semantics expressed in Rust-like pseudocode. So I think it should be operational and not axiomatic like the C and C++ spec to avoid all the problems with that spec. And it is expressed in code and not declaratively, because I think that helps both with accessibility and, of course, it makes it immediately executable. So how concretely does this look like? Well, let's look at the core ingredients of the MiniRust spec, right? There's a grammar, and then there's the operational semantics. So here's the grammar as we would write it down in formal notation. And this is actually probably fine. Most programmers can read BNF. The existing Rust spec even has syntax very much like that. But it is not fully machine readable, not immediately at least. We would have to throw some tooling at that. And maybe we can make it even more blindingly obvious in Rust terms of what this actually is. So we can rewrite this grammar as just a bunch of Rust data types. So we can say a basic block is a list of statements followed by a terminator. Here are some of the terminators that exist in the language. Here are some of the statements and expressions. Because Rust has full algebraic data types, we can just write these down in a very natural form like we would in our idealized interpreter in Haskell, or like in an active data type definition in Rock. We can just write this down in Rust terms, and every Rust programmer will understand without a second thought what all of this means. So we are both precise and accessible to Rust programmers. But of course, syntax is the easy part. We have to also express the semantics. So if we did this formally, we would maybe for an operational semantics describe some sort of state space. And then we would describe a function, or more likely a relation, but could be a function, that computes from one state what is the next state. And so we do the same thing again in terms of, for MiniRust, how do we make this more accessible? Well, we express it in Rust. So the state is just a data type, which has a bunch of fields for all of the components that are relevant for the abstract machine state. And then the next function is just a function which we write in actual Rust code. So overall what this is basically an interpreter. And most Rust programmers, at least like the more experienced programmers, will have already seen an interpreter, might have written an interpreter. So this is like a framework that programmers are very happy and comfortable thinking in. And so we can lure them in by saying it's just an interpreter, and then secretly it's actually a formal spec. But they don't have to know that, right? Because it's actually kind of the same thing when we look at it at this level. So this is the high-level structure of MiniRust. Now I want to get a bit to the bottom of those 2 examples that I showed. So to do that, let's start by taking a look at how memory looks like at MiniRust. Unfortunately, I don't have like a lot of time to go into to demo what the actual MiniRust source code for all of this looks like, but I want to zoom in on one thing. So memory in MiniRust is where we think of memory as there's this one big address space, where Rust is a fairly low-level language. You can do pointer arithmetic. So we actually have to expose the fact that there's only finitely many addresses. This is all kind of visible in the program. So there's 2 to the 64 addresses. And then distributed over this address space are allocations, which are like parts of memory you can actually access. Local variables on the stack, heap allocations, global variables, all those sorts of things. And the data in an allocation is a list of the bytes, which are just the current content of that allocation. And so what you can see here, what's one thing that's interesting about these is that the bytes are maybe not quite what you would expect them to be if like you go to an operating systems class. A byte is not just 8 bits. A byte is either initialized with 8 bits or it is a special magic uninit value, which is just a genuine thing that a byte in memory can be in this model. So this is the picture version. And now, of course, this is not executable and it's not sufficiently precise, so we have to express this properly in MiniRust, and we can again do this with Rust type. Memory is a list of allocations. Every allocation has a base address and a list of bytes, and every byte is either initialized or uninitialized. And this is an enum type, but Rust programmers will understand what exactly this means, and there's no ambiguity. So this is our idea of memory. And now what you might be surprised about looking at this is that there have been no types so far. So in Rust, we made the deliberate choice of making memory entirely untyped, which is different from the C and C++ specifications, because we think this better matches programmer expectations. People go to unsafe Rust when they want to do like weird type layout shenanigans. And so we can't just tell them, oh, you have to follow some sort of typing discipline on the heap, because they would be violating this all the time. And even in C, we see people do -f no strict aliasing in basically every major C program. So in reality is also most C programmers program with untyped heaps. So we make this like officially part of the Rust specification. There's no types here, but still types do come in, of course, in Rust statically for all our great type system things. They also do come in dynamically for the concept of representing high-level values. So in MiniRust, we have a rough kind of mirror of the AST of Rust's types. It's structural and not nominal, but the details don't really matter. The key point is that for defining some operations like arithmetic, we really want to have like high-level concept like a mathematical value sitting there, right? You want to add 15 and 68 or something. You don't want to add just some bits. So we have this concept of a high-level value, which could be a mathematical Boolean, could be a mathematical integers, could be a tuple of other mathematical values. So this is recursive. And this lives like in beautiful math land. But then somehow we have to reconcile this with low-level raw byte land. And so this is where this concept of a representation comes in. This is something you can see hinted at in the C standard. They talk a lot about representation. They never make it very clear what exactly they mean by this. So here's what we interpret this as, what we mean by this, or at least my proposal for MiniRust, is that the representation is really basically a form of serialization. You take your high-level value and you turn it into a list of bytes, just like when you want to take your structured thing and like send it over the network or something like that, right? So there is an encode function which serializes, and there is a decode function which deserializes, takes a list of bytes and returns the corresponding high-level value. And these two functions basically they bridge the gap between the safe, beautiful, happy land and the Kraken bird, right? That's how you go back and forth. And crucially, the lower part here, to go from Kraken back to Ferris, this can fail. Because when you parse something, you might be getting input which is not actually well formed, right? Every deserializer has an error case. And so our decode also has an error case. Okay, so that's the framework. Now let's get back at our example. Remember, there was this I8 weird integer, which somehow defied our logic and mathematics. So we have to understand what happened there, we have to look at what happens when we decode an I8 value. So at this point, we are decoding a single byte, because I8 has size 1, so I've already simplified this a bit, and we have to return this value. So, well, what can we do with the byte? Well, remember what a byte is, it's initialized or uninitialized, so the only thing we can do with the byte is pattern match on it. And now we have to write two cases. Maybe the byte is initialized. In that case, we do the usual 2's complement thing. There's some logic going on for how to turn a bunch of bits into like a signed integer, and like it's not trivial, but it's obvious and solved, and we can just use that. Or the byte is uninitialized, and in this case we raise a parsing error, because uninitialized memory is not a valid representation of an integer. Because which integer should it be? And we could put 0 here, but like, no. So this is just a parsing error. So if we now go to our program, this is very roughly the MiniRust version of the example program I showed at the beginning of the talk. I disabled syntax highlighting because this is now object level code. Everything so far was meta level code. This is now actually in MiniRust. It's a basic block language. Don't worry too much about the details. But also what we do here is we create some storage for X without actually putting anything into it. So X gets some memory allocated to it, but we don't initialize it. And then we test we make our check on that memory. And so if we now go over this program line by line, well, when we run the storage live, we create a new allocation. And the contents of a new allocation are, of course, initially uninitialized. So that's the allocation is length 1. That's where there's only a single byte in that table. And then when we do load X, we call a decode function that we just wrote on this 1 byte, which means we feed uninit into I8 and decoding, like parsing fails. And that at that moment the program crashes and burns, where the interpreter will just say, there's an undefined behavior error at this moment, we don't even have to continue. It just happens to be the case that the compiler still continues and does some garbage, which is okay because the compiler is allowed to do anything once you have undefined behavior. But as far as the spec is concerned, the program already went wrong at that moment, and so later the assertion failure is basically just noise. Okay, so that's the answer for the first demo. What about the second demo, where we had this weird pointer that was like equal but not equal or something? Well, we can already get a hint of what's happening if we look at the docs of the function we've used. We use this wrapping offset function. We actually use wrapping add, but it has the same docs, which says that, okay, so you can use this to do pointer arithmetic, and you're actually allowed to do arbitrary pointer arithmetic. This function itself is safe. It will never cause undefined behavior by itself. But the resulting pointer remembers, in scare quotes, the allocated object that the original pointer points to, and you cannot use it to access anything else. And so the problem that we caused in our code is that we did an offset from x to y, which is a different allocated object, but the pointer remembered where it comes from, and so that wasn't valid. But like, what does this mean in MiniRust terms? How can we make this precise? Well, to make this precise, we have to look at this pointer thing. Right? So what is the concept of a pointer in MiniRust? If you come from hardware, you might think a pointer is just a 64-bit integer. That's actually not the case. It's not true in C, but it's definitely not true in Rust. A pointer in Rust, or at least in MiniRust, is such a 64-bit address, and then some extra magic metadata, which doesn't exist at runtime, but exists for the purpose of specification, which is very much like this uninitialized. It doesn't exist at runtime. It's not a distinction that exists at runtime. Right? I can't ask my RAM, is this byte initialized? They're all initialized. But it's a distinction that's important for the specification. It doesn't affect program behavior, except it defines whether a program has undefined behavior or not, which of course impacts program behavior. So the concrete thing that in this simplified model we remember about the pointer is just the allocation that it points to, which is just an index into this list of all the allocations which are memory. In reality, this thing is called provenance. It's a bit more complicated than just that, but I simplified it for the talk. And so now that we say that a pointer is an option alloc ID, now we can explain how there can be two pointers which are equal but different, right? When you compare pointers for equality, it only checks their address, because that's the only thing we can check at runtime. But actually, for the purpose of specification, there's another part of the pointer that matters, that has not been compared for equality. Those were not the same pointer. They were two different pointers with the same address. And so the equal returned true, even though they weren't actually fully the same thing in the spec. So we solved one problem. We created a bunch of new problems. Which is that, well, now that we have a pointer with provenance, remember we still have to serialize and deserialize all the things we deal with, right? Pointer is now the high-level mathematical value of something of pointer type, right? The same way we have mathematical integers, we now have these like mathematical pointers. So we take this pointer and we want to make it into a list of bytes. Well, okay, we take the address, it becomes an 8-byte number. That's standard, like little Indian, big Indian encoding details, like whatever you want to do for your target. But what do we do with the provenance of the pointer? Well, we have no way to put it in these bytes. And yet when we decode it, we want to get it back, otherwise everything would fall apart. So to fix this, we need to change what a byte is. What we're going to do is we're going to extend byte so that it can hold this provenance data. We're going to say an initialized byte actually isn't just 8 bits, it's additionally, optionally, some sort of provenance if there's a pointer stored here. And now we can write the encode function in a way that it takes the pointer's provenance and just splats it on all of those bytes. And of course, now we've solved this problem, we've created a bunch of more problems. So now we need to say what all of the decode functions everywhere do with all of this provenance. And it turns out the details get interesting, and if you do the wrong thing, you lose a bunch of optimizations, and like it gets complicated. But there's a proposal for what all of these things could do in the MiniRust spec, and there's some sort of design space here and what exactly it should always be. But by writing out the spec in these very explicit terms, and by being forced to write it out like an interpreter, these are questions we will immediately stumble upon, right? We can't forget to answer these questions, which is the thing that happens in C and C++, for example. They added pointer provenance, but then most of the rest of the spec doesn't really talk about what happens with provenance everywhere until Peter Sewell came, and like they spent 10 years figuring it out. And it's not in the standard actually itself. It's a separate technical report. It will probably remain separate, right? Which is not really solving the problem, I would argue. So with this approach, we can't really miss these kind of problems, because our interpreter just won't even compile if we are forgetting to, if we don't talk about what happens with the provenance somewhere. So this approach forces us to not have these kind of blind spots in our spec. Okay, so to conclude, The kind of main MiniRust pipeline looks as follows. First of all, you have to take a Rust program and translate it to MiniRust. We have an implementation of that, but that's not really formal. That's just, like, we just have a tool that does it. So the details of making that formal are somewhere far in the future, but this will definitely be an interesting problem to consider. And then you can run the MiniRust interpreter on this program that has been translated, and the interpreter itself is written in this thing that we call Specker, which is this Rust-like pseudocode I mentioned earlier. You can also think of it like OCaml with Rust syntax. It's some of those things. It's basically a purely functional subset of Rust, and we embed non-determinism into this monadically. And so that way we can express what will usually be a relation as just a single function. And we are slowly moving towards getting 100% coverage of the language. So I have a series of bachelor and master students adding all sorts of parts to MiniRust, because once it becomes a coding exercise, you can give it to a student. And so we now have support for most of the core Rust language features. We have concurrency, but only sequentially consistent concurrency. I'm not planning on touching weak memory anytime soon. But maybe someone has some good ideas for how this could be done. But I'm too scared of weak memory to even contemplate this. There's enough other fish to fry here. There's, of course, also a lot of things to do. Most importantly, I do want to be able to extract these things into rock. I mean, these monadic interpretations kind of lend themselves to some sort of embedding into iTrees in rock or something like that. So this is certainly on the agenda. And a lot of other things to cover more of Rust and connect it with the rest of the ecosystem. All right, so this was MiniRust, which is an interpreter that precisely captures the semantics of Rust and whether a program has undefined behavior. I'm myself also involved in the Rust project, so I kind of can also talk to the people there and advocate for this to become part of the official specifications. I'm head of the operational semantics team, and I'm in contact with the specification team, which is kind of the Rust version of the editor. And generally, so far, the reactions have been very positive. People are excited about actually getting a formal, authoritative spec into Rust. So I think we are on track for this to become, eventually, an actual part of the official Rust specification, fully formal, accessible, and executable, and covering all of the language. And if you want to learn more, there's a GitHub repository here. And also, if you want to do a postdoc in beautiful Switzerland, I have an open position, so please come talk to me. Thank you.
Yeah, John.
Thank you. Really interesting talk. I just saw something flash up on your last slide. You mentioned weak memory models. I'm wondering why you need to formalize that, because I would imagine that anything that would be affected by weak memory would be undefined behavior, but perhaps I'm wrong.
Well, we need to formalize whether a program has undefined behavior. Also, weak memory affects which values you can get when you do an atomic load, so this can actually affect even non-DB programs. And basically, there are all these formal models of weak memory, and there's MiniRust, and we would have to find some way to make them talk. Also, weak memory has a bunch of unsolved problems, like out of thin air. Like, there are formal models, and then there's the reality, and the models actually don't model reality currently, which is not great for a model. So, I mean, there's unsolved problems on several axes here.
Conrad can ask really loud, and you can repeat.
And then you repeat.
You repeat, yes.
So I noticed in your model of pointers that contained provenance. If I'm interpreting it correctly, you're not allowing integer pointer casts to preserve provenance. Is that right, or do you have a concept of like unit pointer t or something?
Right. So the question, the question was that it seems like integer pointer casts would not preserve provenance. I did not talk about integer pointer casts because they are, I think, I recently wrote something online saying they are the PL equivalent of a nuclear waste site. So the model that's actually written down in MiniRust right now says when you cast a pointer to an integer, we put the provenance on a global piece of state called the list of exposed provenances. And then when you cast an integer to a pointer, we pick one of those with angelic non-determinism. I don't think that's actually the end spec we want, because angelic choice unfortunately has a bunch of problems. But I think this is an over-approximation of the end spec we want. I think we want an actual operational spec without angelic choice that is a valid refinement of this thing. But we want programmers to not depend on which refinement we pick so that we can pick better refinements as we go on. That's roughly currently the plan. The Rust documentation just says if you cast an integer to a pointer, it gets some provenance. And it can only get a previously exposed provenance, but we don't tell you which one.
So the claim was that this is more accessible, so now we can tell developers to go read the implementation of a separate interpreter for the Rust language. This doesn't sound accessible to me. How can we improve the accessibility to actual developers rather than telling them to go read a separate implementation?
I mean, you are the expert for that, not me.
Do you have ideas on how we can do that?
No. I mean, in the end, I think it's source code, so we can do like comments and things like that. And then beyond that, I think we'll have to see. I mean, there will obviously be docs and there will be tooling, like you can run Miri or can run this thing, and that should help. I think reading the actual source code probably will only be actually useful for very few. I think reading the definition of what is a byte and like these high-level things, that's very concise and I think very insightful already by itself. So I think for that we can just directly point people at the code. And then for the other things, we'll have to figure out how we can write docs about it. But at least I think this is more accessible than Greek letters. So there is a chance that someone will be able to take this and make it into education material, which might then broaden the scope of accessibility and things like that. So I'm not really an expert on that. But this is, yeah, exactly. Let's talk.
Okay, with that, let's thank Ralf again. Thank you.